All right, here we are at the end of Unit 7. This is section 7.6, and this is a very interesting lesson. We're going to see how much you like this. I really enjoy this. It has a strange looking name. It is named after a mathematician. It is called DeMoivre's Theorem, and it builds directly on what we just did in section 7.5. So DeMoivre's theorem comes from, of course, like everything else in math, actual proof. We're not going to go through the whole thing right here in this video. I will be more than happy to go through part of that in class, and then we can definitely talk about it more after school individually. But for now, I just want to give you a sense of where this comes from. So the purpose of DeMoivre's theorem is going to be to help us raise complex numbers to different powers. Now, usually when we have to raise a complex number to a power, it's a binomial, so we have to box method over and over and over again, and that gets old. So one of the nice things about DeMoivre's theorem is that if the complex number is in polar or trig form, which is why we go through the trouble of learning it, raising it to certain powers is actually pretty simple. So just to give you a very general sense of where this theorem, this formula comes from, let's take a look and start by raising complex numbers to certain powers. So here is some complex number z, and it's being raised to the first power here, r times cosine of theta plus I times sine theta. Z squared then is going to be z times z, and if we go ahead and box method all of that, we end up with, so I'll do that up here, cosine theta plus I sine theta times cosine theta plus I sine theta. Okay, so box method, or just foiling, that's how I learned this, even though I really don't like referring to it as that. But we end up with something that looks like plus I sine theta cosine theta plus I squared sine squared theta. And that equals cosine squared theta. I squared is -1, so minus 1 times sine squared theta. And then plus 2 times I sine theta cosine theta. And if we look at our double angle formulas that we learned a couple sections ago, cosine squared minus sine squared equals cosine of 2 theta. And 2 sine cosine is sine of 2 theta. And then I have an I there. So z squared simplifies to cosine of 2 theta plus I times sine of 2 theta. And if we go ahead and box method all these other ones, we'll end up with cosine of 3. Oh, before I go on, I do apologize. We also have these r's here. R times r is r squared. So here I have r squared times r, that's r cubed. And if we were to box method the complex numbers here and here, we would get cosine of 3 theta plus I times sine of 3 theta. So if you start seeing a pattern, it's because there is a pattern, z to the 4th is going to be r to the 4th times cosine of 4 theta plus I times sine of 4 theta. And so on, and so on, and so on. So that's not an actual proof. Actual proofs in math are a little more difficult than that. Again, we're more than happy to go over that later on. But if we were to formally prove this, we would see that this pattern actually holds for any power of a complex number. And that is DeMoivre's theorem. It's used to raise a complex number to a power. So if we have this complex number in polar or trig form, and it's being raised to some power, some positive integer power, then z to that power, well, that's raising the entire complex number to that power, which equals r to that power times cosine of that power times theta plus I times sine of that power times theta. Okay, so you might be wondering, well, so what? That's a nice theorem. Well, it's actually an incredibly nice theorem because now we get to take a look at a problem like example 1. Use DeMoivre's theorem to find -1 plus radical 3I to the 12th power. Now, ordinarily, think of how much work that would take us to raise that to that power. Even if we use the binomial theorem, which we learned last semester, that's still a considerable amount of work. So instead, we're going to use DeMoivre's theorem. Now, DeMoivre's theorem requires us to have a complex number in polar, also known as trig, form. So this is in standard form. We're going to have to change it. Okay, so right now we have z equals -1 plus square root of 3i. So that's in the form a plus bi. So that means a is -1 and b is square root of 3. Now, we're using the same formulas that we had in the last section. So if you'll recall, tangent of theta equals b over a. And yeah, I need to find theta and I need to find r to be able to convert this complex number into polar form. So that is square root of 3 over -1. Hopefully you recognize this as square root of 3 over 2 over -1 over 2. That's y over x. Excuse me. Now, where does the tangent equal square root of 3 over 2 over -1/2, x, y? Again, we have to take a look at our original complex number because we will get two solutions. We get -pi over 3 and we get 2pi over 3, right? Tangent is negative in the second and fourth quadrant. So your calculator is going to give you an answer of -pi over 3. But is this complex number z actually in that fourth quadrant? If we think about plotting this on the complex plane, -1 and then up whatever radical 3 is, that's actually in the second quadrant. So we know that this has to actually be 2pi over 3. And again, I know that's kind of a leap. This is just getting more comfortable with the unit circle and understanding how all these trig functions fit together. So theta is 2pi over 3. We need to find r. And r is the square root of a squared plus b squared. So that's the square root of -1 squared plus square root of 3 squared, which will be the square root of 1 plus 3, which is 4, and the square root of 4 is 2. So r is 2, theta is 2pi over 2. So put all of that together, and this complex number can actually be written as z equals 2 times the cosine of 2pi over 3 plus I times the sine of 2pi over 3. Now that we've converted it to polar form, we can raise it to a power using DeMoivre's theorem. So let's do that. I want z to the 12th power. Okay, so that's going to be 2 cosine of 2pi over 3 plus I sine 2pi over 3 to the 12th power. Using DeMoivre's theorem, that's r to the 12th power times cosine of n, which is 12, 12 times theta, which is 2pi over 3, plus I times sine of n times theta, which is 2pi over 3. Okay, now I know that looks like a mess, but I promise it simplifies really nicely. 2 to the 12th power is 4,096. Use your calculator. Or just memorize the powers of 2 like I have. Times cosine of 12 times 2pi over 3. Multiply straight across, I'm multiplying two fractions. I get 24pi over 3. 24 divided by 3 is 8. So that's really cosine of 8pi plus I times sine of 8pi. So that's 4096 times cosine of 8pi, that's coterminal with 2pi. And the cosine of 2pi is 1. Plus I times the sine of 2pi, which is 0. 0 times I is 0, plus 1 is 1, times 4,096 is 4,096. And that, my dear honors pre-calculus students, is what I think is some impressive math. We just took this complex number and found that its 12th power is 4,096. Perfectly normal, reasonable number. That's insane to me. That's so elegant and beautiful and interesting. And at this point, you're probably skipping ahead in the video, so I'm just going to move on. In a very similar way, I'm going to ask you to try example 2. And of course, we'll go through that in class. Of course, we'll go through that in class. But for now, sorry, I keep pulling that up. I do want you to try the exact same way that I did example 1. Okay? And we're only raising example 2 to the 3rd power, so it shouldn't be quite as difficult, but we'll see. All right. So that is raising a complex number to a power. Now, if we extend DeMoivre's theorem, again, there's rigorous proof to show that we can use this same idea to find the roots of a complex number. So if we have some complex number, again, written in polar form, then it has exactly n. N is just some number, some positive integer. It has that many distinct roots given by this formula. And this formula is really just coming from DeMoivre's theorem. So the nth root of r times the cosine of whatever our theta is plus 2 pi k over n plus I times sine of theta plus 2 pi k over n. Now you should recognize 2 pi k as a multiple of 2 pi. When we talked about that in previous sections. So adding 2 pi k gave us the general solution for our trigonometric equations. And that's because adding some multiple of 2 pi, which is what adding 2 pi k is, brings us back to that same spot on the unit circle. Now, if we add that over and over again to our theta, and then divide that by whatever the n roots that we're looking for is, this formula gives us those roots. It's really hard to explain this formula without actually proving it. We'll talk about this later on. For now, I want to go through a couple of examples of it so you understand how to use it. So example 3 says, find the 6th roots of 1. Okay, 1 looks like a perfectly normal number. You might ask yourself, well, what are the 6th roots of 1? Isn't that just going to be 1? Not necessarily. So the square root of 1 is plus or minus 1. But I'm asking, what are some numbers that I can raise to the 6th power to give me 1? That's going to include some complex numbers. Complex numbers do some really interesting canceling when you raise them to different powers, as we've seen just in the last example of DeMoivre's theorem. So the 6th roots of 1, we'll first need this number 1 in a complex form, or it is in complex form, I apologize, in trig form or polar form. So z equals a plus bi. Well, what is the real part of the number 1? That's going to be a, that's 1. And then, is there some multiple of I that we're adding to it? No. So that means it's plus 0i. So this is a, this is b. Using that, we can convert this from standard form to polar form. So tangent of theta is b over a. That's 0 over 1, which is 0. Tangent is equal to 0 at 0. And then r equals the square root of a squared plus b squared. Square root of 1 is 1. And again, it's positive because r is the absolute value of that complex number. It is the distance from the origin. So taking this together, our polar form of this complex number is 1 times the cosine of 0 plus I times the sine of 0. And that should make sense. If I try to convert that back, if I simplify this, cosine of 0 is 1. Sine of 0 is 0, so 1 plus 0 times I is 1, times 1 is 1. So I just rewrote the normal number 1 in this really interesting looking complex way. And now I can raise this to different power. Now I can use this theorem to raise it to powers to take the sixth roots of it, and we're going to use this formula now to find the sixth roots. So n equals 6. And notice, well, I'll talk about that once we get to that step. So take this formula, take this complex number together, and we're going to rewrite this. So the sixth roots of this complex number are going to be the sixth root of r, which is 1, right? This is r, this is theta, times the cosine of 0, that's theta, plus 2 pi times k, all over n, which is 6, plus I times the sine of 0 plus 2 pi k over 6. And now, here's where things get a little interesting. So there's that weird k in there. K normally is just any integer. Any integer that we're multiplying by 2 pi so that we get some multiple of 2 pi. So that we can go round and around the unit circle and keep coming back to our same starting position. When we're looking for a specific nth root, then we're not going around and around the unit circle an infinite number of times. We're actually going around the unit circle only up until the nth minus 1 time, or the n minus 1th time, I guess would be the proper grammar of saying that. Starting with k equals 0. So in this case, n is 6, so I'm going to go from k equals 0 all the way to k equals 5. That's 6 minus 1, n minus 1. So now, I'm going to set up 6 different pieces to this to find each of those sixth roots, right? Because the sixth root is going to have 6 different roots, just like the square root has 2 answers and the cube root has 3. So starting at k equals 0, that's 1 times, I'm plugging in for k in this formula, because the sixth root of 1 is 1, times the cosine of 0 plus 2 pi times 0 all over 6. Zero plus 2 pi times 0 is 0, divided by 6 is 0. So that simplifies to 1 times the cosine of 0 plus I times the cosine of times the sine of 0, which is cosine of 0 is 1, sine of 0 is 0, so I get 1 times 1 plus 0 is 1. You might be saying, well, why do we care? What's the big deal? Well, that's the normal root that we would expect to find from 1. But like I said, we are going to come across some really strange-looking complex roots. If we start with k equals 1, we're plugging in 1 for k now. So I get 1 times cosine of 0 plus 2 pi times 1 all over 6. And that's 1 times cosine of 0 plus 2 pi over 6. 2 pi over 6 is pi over 3, so that's 1 times the cosine of pi over 3, plus I times the sine of pi over 3. Hopefully you're getting much more automatic with knowing your unit circle values. And we should get 1 times cosine of pi over 3 is 1/2, plus sine of pi over 3 is the square root of 3 over 2, times I. So there's one of our nice, weird-looking complex roots. 1/2 plus the square root of 3 over 2 times I. If we raise that to the 6th power, we get 1. Believe it or not. Go on ahead, do the box method if you'd like, and you'll see that it works. So we really just keep doing this all the way up through k equals 5. So I'm going to go on ahead and just jot all of that down. If you'd like, you can pause it at this point and try to work through the rest of these yourself. And then go on ahead and skip ahead to where I've filled this in so you can see if it is correct. And that's negative 1/2 plus square root of 3 over 2 times I for k equals 2. K equals 3 gives us 1 times the cosine of pi plus I times the sine of pi, which is negative 1. K equals 4 gives us 1 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3, which is negative 1/2 minus the square root of 3 over 2i. And then finally, k equals 5 is 1 times the cosine of 5 pi over 3 plus I times the sine of 5 pi over 3, which simplifies to 1/2 minus square root of 3 over 2i. And that's it. We have the 6th roots of the regular number 1. And if I raise any of these 6 numbers to the 6th power, I will get 1. Go ahead and try it if you don't believe me, but it works. And you see that we have the familiar 1 and negative 1. But we also have these 4 other really weird-looking complex numbers, which I just think is so fascinating. So go ahead and try example 4 yourself. And I promise again we'll go through that in class. You are going to get some really weird angles there. Use your calculator. Don't be afraid to approximate. You're also going to get some really weird radicals. Again, think about your power rules. Don't be afraid to look and review those a bit. And I do want to draw your attention to one last thing for that example we just went through. Notice that if I had kept going, if I did k equals 6, then I would have ended up with the same thing as k equals 0, right? I'd have 0 plus 2 pi times 6 over 6, which is the cosine of 2 pi, which is the same as the cosine of 0. So that's why we stop at k equals n minus 1, because if we were to keep going, it would just keep repeating through these same 6 roots. All right, so this was quite a section. I know, I'm sure you have a lot of questions. Please jot those down, bring them to class, practice, practice, practice. We will spend plenty of time on this, I promise you. But for now, this is the end of the unit. So go back, rewatch videos, do the practice problems, and review, and come to class. Have an excellent day. Thank you so much.